Okay, so last time we have introduced the Euler class of an oriented Riemannian vector bundle. I remember, so if F is an oriented Riemannian vector bundle, and a manifold M, then we have introduced the Pfaffian and applied it to the curvature matrix of a connection which is metric, so which respects the Riemannian structure on the vector bundle, and with respect to an oriented orthonormal local frame. Then the curvature matrix is skew symmetric, so we can apply the Pfaffian to it, and we get a differential form. And this is the differential form which, up to a factor of 2 pi, represents the Euler form, or the Euler class. So, and the Euler class, and we have the Euler class of this bundle. And now we want to see if we have two bundles. Both oriented Riemannian vector bundles on M, then the sum of the two, so Pythagoras direct sum. So this is also, in a canonical way, an oriented Riemannian vector bundle. So the Riemannian metric on the bundle is chosen such that these two summands are perpendicular to each other, and on each of the two summands we have the original Riemannian metric, right? So that's the canonical Riemannian metric on the sum. And the orientation is such that if you take something, an oriented frame for F and an oriented frame for G, then the concatenation, first oriented frame for F and followed by the oriented frame for G, is then declared to be positively oriented. So this is the canonical way to turn the sum again into an oriented Riemannian vector bundle. So this one also has an Euler class, and the Euler class of the sum is simply computed in terms of the individual Euler classes as the product. This is also correct with the degree. The degree of the cohomology class is given by the rank of the bundle. And if you multiply them, the rank add, and so this gives the rank of this bundle. And why is this true? Well, proof. We can compute a representing differential form choosing a metric connection F and G, and so that number F, number G, in metric connections on F and G respectively. And then the direct sum connection is a metric connection on the sum. So this direct sum connection is such that this splitting is parallel and induced on each of these summands. The covariant differentiation is given by the original covariant differentiations. And now, in order to write down the curvature matrix, we choose a local frame for here and for there. So let S1 to Sn and T1 to Tm be positively oriented orthonormal local frames for F and G respectively. Then, as I said, concatenation of the two is a positively oriented sum. Draw the frame of the sum. And now what can we say then about the curvature matrix? Then the curvature matrix of F plus G for this connection with respect to this frame is then simply the curvature matrix for F is block form and curvature matrix for G. Right? Because of these choices. And if we now apply the Pfaffian to this curvature matrix, actually to the curvature matrix divided by 2i, precise, then this is the Pfaffian of this block matrix. And we have for the Pfaffian of block matrices, we know what we get, namely we get the product of individual Pfaffians. And so this represents the product of the two differential forms of the two different characteristic classes. So that's the proof. All right, good. Now, last time when I studied the Pfaffian from an entirely algebraic point of view, I forgot to prove the most important thing. And no one complained. What's the most important thing that I forgot to prove? What's the most important property of the Pfaffian? I said this thing, but I didn't prove it. It's this property, let A be a skew-symmetric matrix, M by M matrix, and then the Pfaffian of A squared is the determinant. So in this sense, the Pfaffian is a canonical square root of the determinant for skew-symmetric matrices. And how can we see that? Well, if this dimension, if M is odd, then we have seen that the determinant of A is 0. I proved that. The skew-symmetric matrix of odd size has vanishing determinant. And the Pfaffian is also 0 by definition. So in this case, we just defined the Pfaffian to be 0. And so then this equation is trivially true. So the interesting case is that occurs when M is even. So let M be even. And let me first do it in the case when A is invertible. Consider first case A invertible. And well, so let's see. Then we know that by this normal form there exists an invertible matrix B such that B, A, B transpose has this normal form, namely it's of the form as this this canonical form. So let's say this M is even to K, and we have 0 UK minus UK. So get this normal form. In fact, This is possible using an orthogonal matrix, right? And now, what does this imply? Well, then the Pfaffian of this matrix, this we can compute, because then we computed this already. So then, because the Pfaffian of such a matrix is given by mu1 all the way up to μk. On the other hand, we have this invariance property, which we have proved last time, which is given as determinant of B times the Pfaffian of A. So we have that. Okay, that's one thing. And the determinant of A, let's say the determinant of this matrix, is the determinant of this particular matrix, which we can also compute. It's the product determinant of these blocks, and the determinant of each block is 0 minus mu1 squared, so it's the product of the squares. And on the other hand, by the usual product rule for the determinant, this gives us the determinant of B squared times the determinant of A. All right, and now since I'm looking at a case where A is invertible, I know that the determinant of A is not 0, so I can, and B is also invertible because it's an orthogonal matrix, so I can divide by this term, it's not 0. So let me square the first equation and divide by the second equation. And we get that Pfaffian of A squared times the determinant of B squared divided by this one, determinant of A times determinant of B squared is equal to, well, if we square the first one, we get the squares, and if we divide by this, we get exactly 1, right? Or what we have on the right side. And on the other hand, in this expression, the determinant of B cancels, and we get the Pfaffian of A squared divided by the determinant. How we could do that? So if we just, instead of dividing, we could subtract. That's what you're saying? Why not? So if we just subtract, then we get 0. The first one squared minus the second one gives us 0, which is the determinant of B squared times the Pfaffian of A squared minus the determinant of A. Right, so that's, and then we use that this one is not 0. That's true. Yeah, maybe that's more elegant. All right, good. So now this is also completed. Well, so we have that. So the next thing I want to discuss is the following thing. So if you want to compute the Euler form in a practical example, say using local coordinates, for instance, then you need to do this with respect to a metric connection. Typically on a Riemannian manifold, that's not bad because you just take the G-beta connection. If you deal with a tangent bundle, that's okay. But you also have to do it with respect to orthonormal frames. And that's very inconvenient because typically when you use local coordinates, the corresponding coordinate frames will not be orthonormal. And the question is now, how can you compute the Euler or representing form of the Euler class using frames which are not necessarily orthonormal. So that you can use coordinate frames for any positively oriented coordinate system. So let's see how we can do that. And so now to compute the Euler form using non-orthonormal frames. Okay. In order to do that, so we will always have to do geometric connections. There's no way around that. So let nabla be a metric connection of our Riemannian vector bundle F, oriented Riemannian vector bundle F. And now let S1, S equals S1 all the way up to Sn be a not necessarily orthonormal local frame, but it should be positively oriented. Positively oriented local frame. Okay. Now if we look at the curvature matrix of omega, of nabla with respect to this frame, then this will not in general be skew symmetric. So we cannot apply the Pfaffian to it. However, we can look at a modified curvature matrix which involves the Riemannian metric of the bundle. So let G be the metric on A. Let me just give this a name. And then we can look at the sort of the metric curvature matrix, which we now define as follows. So J as a 2 form is defined as apply to 2 tangent vectors x and y. It's defined as take the curvature tensor of this metric connection nabla, apply it to Si, then we get another local function, and then we take the scalar product with respect to G with respect to Sj. And now, if the frame is orthonormal, then this is the same thing as the usual curvature matrix. If S is orthonormal, then this curvature matrix is the same as the usual curvature matrix with respect to this frame. Because, well, what's the definition of the usual matrix? Well, for the usual matrix, what you do is you take this expression here, just to remind you, you take this expression as I, and now you express it again in this basis, right? So you do sum over J, and then you take omega by J x y times xj. And so if this S is orthonormal, then these coefficients occurring in the base expansion are the same thing as these scalar products. But if the basis is not orthonormal, that's of course not true. And so for non-orthonormal frames, the omega G and the omega will be two different things. What's the advantage of this omega G? It has the disadvantage at first that it depends on the choice of metric, but it has a big advantage, namely, it's always skew symmetric. So if this is a metric connection, then this will always be skew symmetric in I and G. So omega GS is skew symmetric as a matrix of two forms. Because for a metric connection, the curvature tensor is skew-symmetric in these two slots. Whereas this matrix here is in general, for non-orthonormal frames, it's not skew-symmetric. So the advantage is we can apply the Pfaffian to this guy. And now it will in general not directly represent the Euler form, but at least we can apply the Pfaffian and see how it relates to the Euler form. Okay, so now in order to do that, let's fix another local frame, which we will then choose to be orthonormal. So let E, E1 up to En be another local frame defined over the same domain, so that I can compare them. And then there's a transition matrix. And now I want to check how these metric curvature matrices transform. It's only Lie algebra valued if your section satisfies if it's a section in the right category, which in this case it means it has to be orthonormal. Otherwise it's not. I mean, you can just see if you, so when I talk about oriented Riemannian vector bundles, then the corresponding connection will be a metric connection, and the frame will be orthonormal and positively oriented. That's then always implicitly understood, because the auxiliary data which I use to compute things like the connection and the frame, of course, have to be compatible with the structure. Otherwise, you have no chance to land in the right thing. But here for the first time, we violate this principle, because I want to compute the Euler form without having an orthonormal frame. And we want to see what happens. The Lie algebra here is skew-symmetric n cross n algebra matrices. Right? Because the Pfaffian, we are applying the Pfaffian, which is only defined as skew matrices. Yeah, exactly. And the good thing is, right, that this matrix is still in the Lie algebra value, to the right Lie algebra, even though the S is not really good. This is why I introduced it at all. All right. Okay, now let's compare. So we have the transition function between the two local sections. So I'm expressing Si in terms of the E case, or E case, T K. So we have this transition function, and let me call it P. More compatible with the notation that I've been using so here in this chapter. So that's B, and I collect these coefficients in a matrix. And now what happens to this metric curvature form? Well, it's easy to see. So if we look at this definition, then let's just write it down. Let's insert this formula. So what we get is the double sum over K and L, B K, B, J, L, and then we have G of E, L. So these are the entries of the curvature metric curvature matrix in this other frame E. The indices L, X and I. So we conclude that this curvature matrix is given by that curvature matrix, and then we have to multiply with B and twice from the left and from the right. and one gets transposed. All right, this is how they relate. And now let's apply the Pfaffian. To that, and we see that we get here the determinant of B times the Pfaffian of that one, and I will scale the curvature matrix by 2 pi because that's what we have in the Euler form. E. And if I now choose the second frame E to be orthonormal, then this represents the Euler form. So let me do this now. Okay, so now under the assumption that E is orthonormal, I have that determinant of B times the Euler form of this metric connection outline. Now this was the definition. In other words, the Euler form can be written as this Pfaffian divided by the determinant of B. Now let's see if we can interpret the determinant of B a little bit better. For that, let me introduce the matrix G, which is defined as the defining matrix for the metric in the basis S, in the frame S. In other words, I'm defining this to be G of Si and Sg. So it's just a representing matrix of the metric with respect to the basis S, 1 up to Sn. Okay, and let's see if we now use this in order to compute this. We can again use this transformation property here. Sum here, yeah, B on K, B L, then we have G of B K L. Now, since the second frame, this E frame, was orthonormal, we know that this one is delta KL. So the sum simplifies to the sum over K, B on K, B J K. And so that's nothing but the matrix B transpose B coefficient of G. In other words, if we take the determinant of G, that's the determinant of B transpose B, which is nothing but the determinant of B squared. So this way we can replace the determinant of B in this formula by the determinant of G. Oh, yes, that's possible. Yeah, I don't care. Yeah, maybe. Doesn't matter. Because we are taking determinants anyway, and then it doesn't matter. That's possible, yeah. In any case, what we do get is that the Euler form is given by this. So I'm using this formula here for the Euler form. So it's given by the Pfaffian of omega gs divided by 2 pi. The whole thing divided by the determinant of B. The determinant of B, by the way, is positive, right? The determinant of B is positive because both frames are supposed to be positively oriented. So the transition function has a positive determinant. Since E and S are positively oriented. And so if we look now at this formula, then we can conclude that the determinant of B is really the positive square root. So therefore, determinant of B is the positive square root of the determinant of G. And inserting this here, we get the Pfaffian of omega GS. Maybe to make the point, I should call this GS because it depends on the frame S. And we have an S here, and also here. And then we have this is to be divided by the square root of the determinant of GS. And now in these expressions, on the right side, the frame E makes no appearance anymore. The frame E is gone. Both terms are just computed in terms of the frame S. So you take the Pfaffian of this metric curvature matrix, which is Q, but you have to correct by this factor here, which is the essential, the square root of the determinant of the matrix representing the metric in terms of the given basis. And this square root, of course, you know well, this occurs in Riemannian geometry, for example, as the prefactor of the volume element when you integrate functions over a manifold. So that's exactly this term that pops up here. So that's how you can compute Euler forms with respect to non-orthonormal frames. All right. Well, maybe, I don't know about a deep reason, but for example, one thing you have to certainly check, and you can do this as a consistency check here, is what happens if you change the metric, you rescale the metric by a multiple of the metric. You replace G by alpha times G, where alpha is a positive constant. Then the metric connection will still be metric for this new metric, so we don't have to change the connection in order to do any computations. And so we can use the same connection upper here for both metrics, the original and the rescaled one. And then you check how do these two terms change. In contrast to the usual curvature matrix, this guy will now change because it will rescale. And in fact, it will rescale by alpha to the size or to the rank of the matrix. Or actually 1/2 of the matrix, because it's the Pfaffian that we are inserting here. So we get a certain power of alpha in front. And which power is it? Well, it's half the size of the matrix, because this is how the Pfaffian scales. And here, same thing. Here you have this guy, this also scales with an alpha. But the power is now the full size of the matrix for the determinant. But then you have a square root, so again you only have half the size of the matrix, and so the two things cancel. So you definitely do have to have such a correction term. You see this from the simple rescaling already. And you will have to have the right power of the determinant, maybe it's square root, otherwise it won't work. And the good thing is that this computation shows this works for all frames and all metrics. Alright, good. Now, a remark that I made earlier already for Chern classes, without really proving it, because we don't have the tools to do that really. And it also then automatically applies to Pontryagin classes. Namely, I made the remark that Chern classes are not just real cohomology classes, they are actually integral cohomology classes. And then of course the Pontryagin classes too, because they are defined using Chern classes. And the same thing holds for the Euler class. So the Euler class of a bundle on a manifold M is actually, so if this is of rank M, this is the cohomology class of the base manifold, not just with real coefficients, but actually with integral coefficients. And so what this means is if you integrate this cohomology class against any integral cycle, then you get an integer. If the manifold is a compact manifold, that's actually a consequence of the Gauss-Bonnet theorem. Because by the Gauss-Bonnet theorem, if you integrate this guy over the fundamental cycle of M, then this will give you an integer, namely the Euler number. And if you have a compact, connected, oriented manifold M, then the fundamental cycle generates this integral cohomology. So any other cycle is homologous to a multiple of the fundamental cycle, and then by the Gauss-Bonnet theorem, you get again an integer. Yeah, so, but anyway, so that's the same statement as for Chern classes. From this, once one knows this, one can answer a question that was asked last time, namely, does the Euler class actually depend on the metric of the bundle? It certainly doesn't depend on the orientation, because if you flip the orientation, then the Euler class must get a sign. You see this also from the Gauss-Bonnet theorem. If you flip the orientation, the integral becomes a sign, but it has to give the same result as before, the Euler number, so the integral must also flip sign. But does it depend on the metric? And the answer, so consequence, and the answer is no. This Euler class is actually independent of the Riemannian metric. And you may consider this as a deeper reason why this computation is possible without, even for non-orthonormal frames. Because it's, the construction uses the metric because the Pfaffian is defined only for skew matrices, but actually, and the corresponding Euler forms do depend, but the class does not. And why is that? Well, if you have two metrics, so let G0 and G1 be two Riemannian metrics on the bundle, then we can interpolate between them. So then put GT to be 1 minus T times G0 plus T times G1. Then for each T between 1, 0 and 1, this defines the metric. So we have a continuous family of metrics joining G0 and G1. So each GT is another Riemannian metric on F. Now we choose metric connections. Choose metric connections. Nabla T for GT, and should also depend smoothly on T. And you have to think a short moment why this is possible. Why can I find metric connections which depend smoothly on T? If the metric depends smoothly on T, like here. But anyway, you can do it. And then from this, we will get for each metric GT and the corresponding connection nabla T, we will get a corresponding Euler form, right? Then nabla T, the corresponding Euler form, and this then depends also smoothly on T. Because what you do is you compute the curvature from this. This will depend smoothly on T, and then you take certain algebraic combinations of these entries, and you get something which may look complicated, but it will depend smoothly on T. Okay, and then We pass to the corresponding homology class. In Hn of our manifold. So then this is also smooth. But now the point is, this is integral valued. And this is a discrete subset of this real vector space HMR. So that's a discrete, sitting discretely in it. And since it's continuous, then it must be constant. And so this way we see that the homology class, so the Euler class, does not depend on that. All right, good. That. So the next thing is to compare Euler classes and Chern classes. Okay. So let's start with a Hermitian vector bundle. So let F be a Hermitian vector bundle of complex rank n. Now, we can consider this as just a complex vector bundle, so we can forget the Hermitian metric. Then consider this as a complex rank n vector bundle, and then as such it has Chern class. Right? So, F considered as a vect MC bundle, complex vector bundle of MC, as Chern class in the homology, the even homology of M. So this is when we just forget the Hermitian scalar product. On the other hand, we can also forget the complex structure and consider it as a real bundle and take the real part of the metric, which gives us a Riemannian metric. This way we can consider it as a Riemannian vector bundle of rank 2n. And the complex structure induces an orientation also. So the bundle, so we've earlier called this the realification. So forgetting the complex structure, just considering it as a real vector bundle carries so the Riemannian metric a real part of H, if H is the Hermitian metric, so let me call this G. So Hermitian metric is called H. And the real part of Hermitian metric is always a Riemannian metric, the Euclidean scalar product on the underlying real vector space. That's one thing. And the complex structure, we haven't completely forgotten it because it induces an orientation too. So, and an orientation. And the orientation is such that if S1 up to Sn is the local complex frame, right? The complex rank is n, so a local complex frame, then S1, I times S1, S2, I times S2, and so forth, all the way up to Sn I times Sn. This is then a real basis, and this is declared to be positively oriented. If you replace this by another complex frame, this will not change the orientation. So then this is positively oriented. This is how you use an orientation from a complex structure. So in other words, to summarize, we can also consider F as an oriented Riemannian vector bundle. The real application is an oriented Euclidean dimension 2n vector bundle. And as such, it has an Euler class. So, and this is now sitting in H2n. Okay. Right. Question, are these two things related? And if they are related, then, well, they could be related to one component in here. 2n is even, so that's good, right? So then we have to look at the corresponding part of degree 2n in here, which would be Cn. And indeed, Cn and the Euler class are the same. So proposition, the Euler class of Fr is the same as the nth Chern class of the original complex form. This is how they relate. In this situation, where you have them both available. Of course, in general, the Euler class is also defined if it's not coming from something complex. Let's do it first in case that F has rank 1. It's a line bundle. If it's a line bundle, then, so it's a Hermitian line bundle, and well, let's take a metric connection on it to compute the Chern class. We could take any connection to compute the Chern class, but we can also restrict ourselves to metric connection. So let nabla be a metric connection. On F, and let S, now it's just rank 1, so it's just one non-vanishing sector, so it's just orthonormal, so that means we have a local section of length 1. Let S be a local section of length 1. So that's our orthonormal frame. And then we can compute the curvature form and of nabla with respect to S. And how does the curvature matrix then look like? Well, the curvature matrix when applied to S is the same thing as the curvature tensor applied to S, right? So the curvature tensor is an endomorphism applied to S, and this is one-dimensional, so we get it just by multiplication by some scalar, which is omega of x and y. And what can we say about this omega? A priori, depending on x and y, this is some complex number at each point. However, we are using a metric connection and an orthonormal frame or unit length section. So that means if we insert, what it means is that this guy takes the values in the corresponding Lie algebra, to put it in fancy words. And what's the Lie algebra in this case? What's the structure group? The structure group of a Hermitian vector bundle, what is it? Skew Hermitian, exactly. And so in this case it's rank 1. So, so this guy takes values in the Lie algebra of U1, right? So skew Hermitian 1 by 1 matrix. And what is that? Complex 1 by 1 matrix Q. It's a 1 by 1 matrix. It's just a number. So what does it mean to be skew? Exactly, so it's purely imaginary. That's what it says, right? So this is, if we were real, then you would be right? If we were real, then this would mean 0. But it's purely imaginary. So this is a purely imaginary form. It's a two form of the form I times a real 2 form. So that's what we have. Okay, good. And so maybe I can, so let me write it like so. Omega is equal to I times, now what letter could I take? I, where omega I is the imaginary part, if you like, so that's a real 2 form. So this is defined only locally, not on the whole manifold, right? So only where the frame is defined. Oh, write it like this. Real 2 form. U is the domain where the section is defined. Okay, good. So we have that. Now, this is what we have when we look at it as a complex bundle. Now, how does it do things look as a real bundle? And well, S, IS, so that's a local frame, a positively oriented local orthonormal frame for the as a real, right? So that's positively oriented, because this is how the orientation is defined. It's positively oriented, orthonormal. Local frame, real local frame. And why is it orthonormal? Well, they both have length 1, certainly. And if you take the scalar product of the two, then what is the scalar product? You have to put this in the Hermitian product, and then you have to take the real part. But this, the Hermitian product of this is I times the Hermitian product of S and S. The Hermitian product of S and S is positive, and I times that is imaginary. If you take the real part, it's 0. This is why these two things are perpendicular. Yeah? Because the Riemannian metric here is the real part of the Hermitian metric. That's all. So they have length 1 and are perpendicular. So it's really an orthonormal frame when we consider it as a real frame. Okay. And now we can consider we have to compute the curvature matrix of Nabla with respect to this frame, because this is what we have to insert in the Pfaffian to get the Euler form. Okay, so what is it? Well, the curvature tensor, the connection is the same for both. It's Nabla, and the curvature tensor therefore is also the same. So this, as before, is just I times omega I x y s. So let me write this I here. So then this is is now instead of s here. And similarly, r of x, y applied to is. This is coming from a complex connection, so that's complex linear. So we have I times omega x, y, is, which gives me minus omega I x, y, s. So therefore, the curvature matrix is a 2 by 2 matrix of nabla with respect to this frame. Curvature matrix is then given, let me call it omega tilde to distinguish it from the original curvature matrix. This is now S is mapped to omega I times IS. So we get an omega I here. And IS is mapped to minus omega I times S minus omega I. So that's the matrix. Alright. Now the Pfaffian of this guy normalized by 2 pi. This is now Pfaffian of this matrix. And what is it? Yeah, so if I have a 2 by 2 matrix, the Pfaffian is symmetric, the Pfaffian is the right upper corner. So this is omega I and 2 pi. And the Chern class, first Chern class of the original curvature, also normalized, but this time by 2 pi I, because this is what we have in the Chern class. This part. So here we have the omega, so omega is I times the omega I, and because of this factor, the little I in front cancels. Chern class, so that is exactly the determinant in this case, which is the determinant of omega I on 2 pi, and that's a 1 by 1 matrix determinant, so that's gives me just omega I on 2 pi. And so it's the same thing. So this proves it for rank 1 bundles. Now, higher rank bundles. Let me look at the case where our higher rank bundle is a sum of line bundles. It's of higher rank, but still can be decomposed into line bundles. Now, so we look at the case that F is the direct sum of L line bundles. Right? So where these are line bundles, complex line bundles, complex condition line bundles. So let's see. If we look at the Chern class of this guy, then we have this multiplicative property of the Chern class, which says that this is the Chern class of L1 times the Chern class of Ln. And so that's just a line bundle, so we have 1 plus C1 of L1 times and so on, 1 plus C1 of Ln. And if we expand this, we're really only interested in the thing of degree 2n, so in the nth Chern class. So we get 1 plus, our first order term would be the sum of the C1s, but this is not our concern. The highest term that we can get is the product of these C1s. So that would be C1 of L1 times C1 of Ln. So that's the degree n part, right? That's the part in degree n. Or in other words, Cn of f is the product of C1s. And how about the Euler class? Well, the Euler class we have also seen that this is just how the Euler class behaves under sums. Namely, It's also multiplicative. So it's the Euler class L1 up to Euler class Ln. And for rank 1, we have just shown that it gives us the same thing as the Chern class, first Chern class. By the first case. So that's the same thing. Okay, good. And now for the general case, F general rank n Hermitian bundle. Okay, there are now two ways to argue, an elegant way and a down-to-earth way. And let me first explain the elegant way. This is based on the so-called splitting principle. And before I apply the proof, let me just mention what it says. Splitting principle. Very roughly it says, when you do computations with characteristic classes, you can always assume that the bundles split into line bundles. More precisely. There exists, so given a rank n, or let's say a vect NC bundle on a manifold n, then there exists a smooth map pi from some other manifold P to M. So P is some other manifold of higher dimension than M. In fact, this can be realized as a fiber bundle, but that doesn't matter really. So smooth map such that the following two things hold, such that first, the induced map on cohomology is injective. So pi star, which goes from cohomology of M to the cohomology of P. So this is injective. And secondly, the given bundle that we have here, when we pull it back to P, it decomposes into line bundles. So pi star of F this can be written as a sum of n line bundles. So in other words, the bundle does not necessarily split into line bundles on the original manifold which we started with, but we can pull it back to a larger space where it does decompose into line bundles, and this is in such a way that the cohomology is like an injection. So this is injective. So let's see how we can use this now. And if we find the time during this lecture course, proof the splitting principle, but at the moment, let's just apply it to see how useful it is. So in the general rank n bundle, so let's apply the splitting principle. Apply splitting principle. And then we have the following. The Euler form of our original, or Euler class, of our original bundle F on the manifold M, if we pull it back, then this is a characteristic class, so it's the same thing as the Euler class of the pullback bundle. I didn't say this explicitly, but it's like for the Chern class and the Pfaffian class, because you can just pull back the representing forms. So it's also a characteristic class. The Euler class is a characteristic class. This is naturality. And now this bundle decomposes. And in this case, we have proved that this is the same thing as the nth Chern class of the sum. Which is the nth Chern class of the pullback of F. And Chern classes are also natural, so I can pull the pi star back out. And this gives me the nth Chern class of F. And now, so this did only used the naturality of characteristic classes and the fact that we have proved it for sums of line moments. And now we use that pi star is injective, right? So since pi star is injective, we have that the Euler class is contained is the same as Cn of F without pi star, which is very hard to show. So now you believe me that the blitzing splitting principle is useful. If you want to avoid it, you can do that too. Then you would proceed as in step A, which I have erased apparently. But then you have, rather than looking at 1 by 1 and 2 by 2 matrices, as I did in the rank 1 case, you have to look at the general case, and then you have to invoke certain more complicated identities for Pfaffian, which I did not want to discuss. And how to relate it, then you have to do, So then you get it. In the rank 1 case, if you do it directly by hand, if you like, then you get a curvature matrix, omega on the complex side, which is complex valued. It takes its values now in UN, right? It's a Hermitian matrix valued, but it has real and imaginary parts. And what you want to identify is the determinant of this guy divided by 2 pi r, right? So that's what gives you the Chern class. On the other hand, so this is with respect to a complex frame, S1 all the way up to Sn. Now you go to the real side. You have to manufacture out of this a real basis, and the simplest thing to do is to take this basis, because then if you write omega as a real form plus I times an imaginary form, then the corresponding curvature matrix on the real side for this thing will be omega tilde. And now you have something like omega r, omega I, minus omega I, omega r, something like that. And now you want to look at the Pfaffian of this guy. And you want to compare it with the determinant of that guy. And you have to show that these two things are the same. We have shown a special case of this formula, namely when this real part is 0, then we have shown that the Pfaffian of something of this form, so this is then symmetric, this guy. We have shown that the Pfaffian of A0 minus A transpose 0, that this is the same thing up to a sign of the determinant of A. And so this happens when the real part is 0. And then this part will then contain only the imaginary part, and the I is again divided out by this little I. Then this would give us the result. But in general, this guy is not 0, and then things become more complicated. Then, but in fact, there is a sign here, if you remember, n times n minus 1 on 2. But this gets compensated because this is not necessarily positively oriented. We have to do switches to put the I S1 behind the S1 and so forth, so this will then cancel the sign again. So that's also one thing you can do. But it's a bit messy, and I didn't want to go into this, and I wanted to present the splitting principle and see how useful it can be, so that you don't have to get involved in this, in fact. Questions about this? No. No? Good question, but the answer is no. And in fact, on the exercise sheet that you will get today, directly after this lecture, you will see that the Pfaffian classes and the Euler class are totally independent from one another. You can find examples where one thing is trivial and the other one is not trivial, and vice versa. So they are not related. There's no general relation between Euler classes and Pfaffian classes. It's a new thing. Okay, I guess I stop here for today.